Hello guys, welcome back to my video lecture series on the Black-Scholes derivation, and this is going to be the 13th video where we will be discussing a multivariable Taylor expansion. So just as a recap, in the previous video we expressed a Taylor expansion in the following way. For a single variable, so we said that f of x is going to be equal to the infinite series from n is equal to 0 to infinity of 1 over n factorial times d to the nth derivative, f of x to the nth derivative, dxn times x minus a n. And with some algebraic manipulation, we also found that we can represent this in a differential form, df of x, which is going to be the infinite series from n is equal to 1 to infinity of 1 over n factorial times dn dxn, the nth derivative of f of x times dx to the power of n. And this is going to be for a single variable function f of x. Now, if we want to talk about a multivariable system, we're dealing with two or more parameters, x and y. And as you can see, this resembles our option price or our premium price as a function of s and t. Now, to do this, essentially for our first term, we would have our df as a function of x, sorry, not just x, of x and y in our Taylor expanded form. We would have two kinds of first derivatives. So we would have the partial derivative of f with respect to x times dx plus our partial derivative of x with respect to y dy. And this is going to be our first term. And then we can add that with our second term, which is going to be the second partial derivative of f with respect to x plus our second partial derivative with respect to y. And there's actually two more ways to do this. We can add this with our partial derivative of f with respect to x and then y. And we can add this to our partial derivative, our second partial derivative with respect to y and then x. And obviously, since this is the second term, it'll all be multiplied by 1 over 2 factorial, which is just going to be 1 over 2. Now, if you've taken a course on multivariable calculus, you'll notice that these are essentially the same thing. So we can write this. If you differentiate a function with two independent variables with respect to x and then with respect to y, that is actually going to be equal to the same function when you differentiate it with respect to y first and then x. So the second term we can actually rewrite as follows. So I'll just bring the 1/2 out here. I'll have our d squared f dx squared plus d squared f dy squared plus 2 times d squared f dx dy dx dy. And this is going to be our second term. And the reason I'm going over the first term and the second term is because when we apply the quadratic variation of Brownian motion, we will find that the second term of the Taylor expansion is actually important when expanding out a multivariable process that depends on a stochastic process. Our stochastic process being S of t. And essentially, like we discussed before, what we're going to do with this is find dv. So essentially what we're doing is we want to differentiate a stochastic process, and this is when the second term of the Taylor expansion is necessary. And this process of differentiating a stochastic process actually has a name, and that would be discussed in the next video, and that's called Ito's lemma. And this is a formula that's found in something called Ito calculus or stochastic calculus, just because of the quadratic variation of Brownian motion, the fact that the differential of Brownian motion is actually equal to the square root of dt requires a completely new branch of calculus, which is called stochastic calculus. And this is a very advanced course that's typically not taught to undergrads, and Ito's lemma is just a small fraction of what is actually taught in this huge and very advanced course. But for the sake of deriving the Black-Scholes model, we are going to need to use Ito's lemma to find dv. And we'll do that in the next video.